Good evening, one and all. I welcome you to the sixth live session of NPTEL course, Production Technology Theory and Practice. The teacher for this particular course is Professor Shonak Kumar Chaudhary, IIT Kanpur, and this is Arnab from IIT Madras, and I am being assigned the TA duty for this particular course. So I expect that you have gone through the video lectures of the previous week, and we shall be discussing a few questions pertaining to those video lectures and also a few questions related to previous weeks, that is, fourth week's problems. Okay, so let's start then. Coming to the first question, the question is related to the operation of a strain gauge during machining, and the application of a strain gauge during machining while calculating the forces that are acting on a tool. So suppose we have a tool which is being placed in this way. We try to replicate the 3D image of the machining operation. Then this will be your rake surface, and this particular the surface that's facing away, it's the flank surface, and it is interfacing the workpiece somewhat like this. It is being imparted a rotational motion, and the tool is imparted a feed motion. So this can be modeled as a cantilever beam. So this is like held to the tool post basically. So this can be modeled as a cantilever beam, which is subjected to a normal load that replicates the cutting force. And if we see this particular beam from the top view, then you will also have a transverse load which replicates the feed force. Okay, so there will be actually the force that will be acting at this point. If this is the cutting force, and thrust force will be somewhat like this. So this thrust force can be further divided into two components. One is along the feed direction. So one force will be along the feed direction that we are denoting by F subscript small f, and the other will be perpendicular to the depth of cut. Sorry, it will be along the depth of cut. So I am denoting it. This I am denoting by x, since this is x-axis, and this by y. Since Fy is this radial force component is significantly smaller compared to other force components, that's why we it's generally smaller, so we can neglect it. Otherwise, we can also incorporate that, so that force will be somewhat like this. So this will be my Fx, this will be my Fy. So we can see that there are three force components which is acting on this cantilever beam. So if we come to the first one, that is the cutting force, which is nothing but Fz. So here the cantilever, this force will try to bend the cantilever beam like this. And now, if suppose we place our strain gauge somewhere here and one on the other side which is not visible, then we will see that, okay, sorry, let's remove this one for now. We have a strain gauge here and another strain gauge here, the top and the bottom. Now if we see that due to this force Fc, there is one, so this is my cantilever beam, So due to this load Fc, there is a tensile stress on the upper surface and there is one compressive stress on the lower surface of the beam. I hope you agree with me on this. So due to this tensile stress, the strain gauge is experiencing a strain along, like it is a tensile strain, so I'm denoting it by epsilon t, and the strain gauge which has been placed at the bottom, that is experiencing a compressive strain which I'm denoting by epsilon c. Essentially these two will be same if we consider this to be neutral plane, and if we revisit the strength of materials, this relates strength of material with machining. So then we can say that the stress the stress profile along any section will look like this. Along any cross section will look like this. So this is your sigma T max, and this is your sigma C max. Now the question asks that for a 15 mm by 15 mm square cantilever beam, so we know that the cross section of this particular beam is square. So now it is being subjected to 200 Newton load. So we have F is equal to 200 Newton. Now we are not being said that what is the direction of this. Okay, so we are said, we are told that it is a normal force of 200 Newton. So it is basically Fc in this case. So you have said that F is equal to 200 Newton, and the strain multiplied by 10 to the power minus 5 times, you need to find that at a distance 20, if the strain gauge is placed at a distance of 20 mm from the point of application of load. So you have said that this distance from the line of action of the load till the strain gauge, that distance is 20 mm. Okay, so you have a formula. If you go through the videos, you will see that there's one formula which is being used and implemented directly. So that is like 6F into L divided by EBH square. So where is this particular expression coming from? So it's a small derivation. I will try to do that. Before that, let me just revisit this particular thing. So this is my side view, and this is my top view. So from top view, we can see that this particular beam which replicates the cutting tool, it's experiencing a compressive load Fy and lateral or transverse force Fx. So due to the action of Fx, it will try to bend in this direction, and due to Fy, it will try to compress. So I am exaggerating this effect. This deformation values will be very less. As we are finding out epsilon, you can pretty sure like estimate how little this deformation is. So here also we will see that this particular region is experiencing tensile stress, and due to this bending action of Fx, and this section is experiencing a compressive stress, but this is being superimposed with the compressive load due to Fy. So somehow I'm like I'm just adding this sigma c dash, which is due to the effect of Fy. So if we know that this compressive loads will be negated, like it will be negative, so this positive sign will automatically turn into negative if we add this, and this both are negative, so they will add up ultimately. Anyway, I'm not going into that details. If you are being asked a problem where you are given the like you are being asked to calculate the forces in Fx, Fy, Fs, I mean, you're not asked to calculate, rather you are asked to measure the forces in fx, fy, fz direction, then this will be your ideal approach using the strain gauges. So coming back to this particular expression, where from is this coming? So if we remember correctly, if this was my cantilever beam and this is your force P at a distance L, say this is the line and this is your neutral plane. So your stress distribution will be somewhat like this. So now at this point, say this is point X, this is point Y. At point Y, if we try to transfer the load, so this is equivalent to a condition like this. This is my X, this is my Y. So we have a point load P and that is being added with a moment which is equal to P into the distance between this X and Y, that is L. So this is the moment and this is the normal load P. So what did we do? We just transferred, or rather transferred the load from point X to point Y, and then we drew the free body diagram. So it's not actually a free body diagram. In that case, you have to remove this support. But yeah, we can say that this both are equivalent to each other. Now, if we try to um, calculate the stress, then we can write. Sorry. Now, if you try to calculate the stress, so we have this bending expression, sigma by y is equal to m by I is equal to E by R, right? So we will be using this part. Basically, at y, we have m is equal to p into L. So my sigma will become m into y by I. So y, what is y? Y is the distance from the neutral plane where you want to find the stress. In this case, we want to find the maximum value of stress. So y will be nothing but, so if we consider this cross section as like this particular value as h, then y will be h by 2, right? So yeah, you substitute that. So m will be nothing but pl, y is h by 2, and what is I? What is the area moment of inertia for this particular beam, for this particular loading condition? Yeah, Akshay, I can see that you have joined. So can you tell me what is the value of I here? Hello, am I audible? Hello?
Yes, sir, you are audible.
Yeah. So Akshay, what will be the value of I for this case?
In this case, we
So you have a rectangular section. This
square
is the
cos
axis. th- Yeah, if this is B and sorry, this is B and this is
ph
H.
cube by 12, sir.
Yes, BH cube by 12.
Yes.
Yeah, so this 2 and this will cancel out. H, this will be left with H square. So you will get 6 PL by BH square, right? Now, if you try to find out the strain, so this gives you the, suppose this is the beam and this is that section Y. This gives you the stress at this particular region. Okay. So what is your strain gauge basically doing? Your strain gauge is placed somewhere here. So your strain gauge is experiencing a strain due to this sigma, and as a result it is experiencing a strain, say epsilon, and as a result it's exhibiting a change in voltage which we are measuring, and we are doing a calculation method to calculate the load, that is P. Right, that's what we do in case of dynamometry. So now it's like epsilon can be written as sigma by the Young's modulus E. So from here we are getting 6 PL by EBH square. Okay. So this is the final expression of the strain that this particular strain gauge is recording as a change in voltage. Okay. So in this question, like since this question is being taken from the previous year's assignment, and this relates to machining, so I explained this in terms of machining and all. Yeah, so do you have any doubt regarding this?
Yes, sir. In this question,
Hmm.
the value of E was missing,
Value of E is missing, yes, right.
and in this regard, I asked a question on forum also, but it
Okay,
was not
so
answered. So because of that, I have neglected the value of E and solved the
that
question. So
so with
it was.
neglected means you didn't what value of E did you put?
I just considered it as one. So for that reason, I got the value of 7.11 as answer.
So do you think it is a correct approach? Suppose you are not given with a value, then what should you
No,
do
but
ideally?
yes, but I considered it as 100 GPA.
Yeah, you can
So,
consider it as a
so
as a
because
value
of
that
that,
is, yes, yes. So basically, in such cases where you are not given with a value, you are expected to assume a value for a real scenario. Suppose if we are machining a particular material,
Mhm.
so generally what tools do we use? So this, if you consider this problem to
They can
be,
just
yes, related with machining. Now,
Mhm.
from reading from the question, you can't understand whether it is a problem of machining or not. But in case you are given with a problem of machining and some data is missing, in that case you should assume certain values, write it down. So
Yes, yes.
your the examiner, like the paper, the one who will be setting the paper, he will be also expecting you to do such things. That's why I'm just reiterating this.
Yeah, yeah, yeah. I understand.
Okay, so this is a straightforward question. You just plug in the values, you will get the answer. But what I wanted to discuss is a more realistic scenario. That is this one. I think you can see this box portion. So this is more realistic scenario where I said that your tool, which is experiencing a cutting force, thrust force, and feed force, right? Ideally. So in that case, if you are having strain gauges, then what will be the first question will be how you would like to orient them, how you would like to place them. So you would like to place them at a distance L, say. So you need to see at what distance L you are getting, the data is sensitive enough to measure the force. So the strain should also be high there, high enough to calculate your force value to be recorded and as well as to calculate. So yeah, to measure FC, your two strain gauges will be placed like this. To measure Fx, that is in the transverse direction, if we try to draw in the first figure, then it will be perpendicular to the plane somewhere at the point where I am pointing right now, this blue point. So your strain gauge which is required to measure that should be also placed like this, right? So if this was you know I would rather denote it by this blue color, sorry, green color. So since this is the top view, so this will be the placement of your strain gauges to measure Fx. Similarly, to measure Fy, how should you place the strain gauges? So you have measured Fx, like you have made arrangements to measure Fx and Fc. How will you measure Fy? It is a compressive load on the tool, which is this one, this Fy, the radial force. So for that, you need to place four strain gauges in the following manner. Say, I'm showing it with the red colored pen. So you need to place two diametrically opposite strain gauges, which like the green ones that we are showing here, they can also be used, or you can also place two separate strain gauges which are diametrically opposite, and also two circumferential strain gauges which are diametrically opposite, like one here and the one on the other side. So if this was my cross section, so I would have to put two circumferential strain gauges like this. Sorry, it won't be two strain gauges like this and two like this. So what happens if due to this Fy, this and all these four strain gauges will be activated, and they will record some change in voltages, and from there you can through some calibration you can find out Fy. Along with that, you can also know uh, if there is some, if you want to isolate the effect of bending, then you can also do that. Anyway, this is also possible by using the present arrangement. So essentially, this the reading that you will get from this green colored strain gauge is of the thrust force. Like, since Fx and Fy both will lead to bending of the tool, so the force that you will be getting, that is of the resultant of Fx and Fy rather than only Fx and only Fy. Okay, so moving on to the next question. In an octagonal ring type dynamometer, the tangential force is measured by the gauges. By gauge we mean strain gauge, which are placed at an angle of what? With respect to the vertical axis. If you have gone through the lectures well, then you can relate this, that for octagonal ring type dynamometer, we have a setting similar to this one, is fixed here, this dynamometer, and we are placing the tool. Sorry, you can place the workpiece also, you can place the tool also, it depends on the setting. So you're placing it on top of this post, on top of this dynamometer. So suppose it is experiencing a load like this, which is a normal load, and at the same time it is also experiencing a load like this, which is a tangential load, Ft and Fn. Okay. So this will be your dynamometer. So you're being asked about this particular angle. By the way, for this type of dynamometers, you place the strain gauges like this. So these four dynamometers are used to measure Fn. And these four dynamometers, sorry, these four strain gauges rather, are placed to measure Ft. So you have been asked this particular angle, the angle that this you know the tangential force is measured by placing the gauge. Yeah, at what angle this gauge is being placed with respect to the vertical axis. So this angle is 50° in case of octagonal ring type dynamometers. In normal ring type dynamometers, this angle is 39.6°. So how do we calculate this, or rather how do we ascertain these values? So we generally place the strain gauges such that we get sensitive reading out of it, so that with small changes in this particular loads, it records a change in voltage, and we can measure that, and from there we can calculate the value of forces. So one, it should be sensitive. So now the thing is, you need to place the strain gauges such that it records the values, and without getting damaged, or getting unstable. So through elastic studies. Photoelastic means basically you make a transparent to light, some setting which you make transparent to light, and from there, during this loading condition, you with the same geometry, you send light, and you check where the strain is maximum. So through that photoelastic studies, it has been found that at this particular angle of 50 degrees, in case of ring type dynamometers settings under this particular loading conditions, at this 50-degree angle, the strain is maximum. The strain recorded at this particular angle is maximum. So that's why we are choosing that particular position. Okay. The next question, the relationship between the magnitude of cutting forces and the deflection in a dynamometer is called what? So if the dynamometer is experiencing some force, say I am assuming a ring type dynamometer, and it is experiencing some value of force, or some force F. So this is the tangential and normal components. Now under this force, it will try to bend like this. So if you are removing Ft, say we are taking only Fn, so it will try to assume a shape like this. So now see, so this particular, we can say a deflection is happening, and we are say, quantifying it by delta, say. So now we need to ensure that during this regime, that from 0 to delta, during this deformation, the F is directly proportional to delta. Otherwise, suppose this relationship is not linear in this particular range, then you won't be able to calculate the value of, like, linear means, um, if the material is such that it doesn't follow this linear relationship, then you won't be able to calculate it using the measured values of voltage changes. So one, you need to know the exact relation between the force and the delta, and the deflection, and second of all, the voltage signal that it is sending due to this deflection, that also needs to be calibrated. So suppose the material is following a hysteretic loop. Suppose during the loading it is going like this, and during unloading it is coming like this. So due to hysteresis, it is storing some amount of energy. So mm, uh, for this type of material, you can't be using it for the dynamometry or force measurement. So you need to have a linear relationship between F and delta. This is the loading part, and this is the unloading part. Why do we implement a thin ring in ring type dynamometers rather than a thick one? So if this is your ring, then if say this is your ring thickness T, then why do we consider it to be a small, like we use a smaller value of T rather than a larger one? If we see the expression of strain for this particular dynamometer, so say for ring type dynamometer at So you have the strain gauges which are placed here and here to measure Fn. So if we see the expression of that, it's directly proportional to F R by EBT square. So where R is the radius up to the mean line, that is up to the pitch circle. If we calculate the radius, then it is R. B is the width of this particular ring. If you see through this, like in the other plane, so if you see like this, you will see it has got some width, so that is B. And T is the thickness of this ring, as I have denoted here. So if you can see here, E is related to T, like it is inversely proportional to the squared of T, right? So if you choose a smaller value of T, you will get a higher strain, and you want that, so that to measure even small forces you can use it, right? So that's why you choose a thinner ring rather than a thick one for making such ring type dynamometers. But it should also be like it also should be kept in mind that under the action of this force, this particular ring is not behaving as a history, like it is not undergoing any hysteresis, or second of all, it shouldn't buckle, like due to this load the ring shouldn't become something like this rather than a oval shape. So those things should be taken care of, and that's why we do go for smaller values of T, but it should also be optimized to some extent, and it also shouldn't fail under the action of this load. Circular ring structures by itself are not useful for a dynamometer due to, so what are the disadvantages? We said that due to the action of this load P, what can happen to this ring? So if we along with this normal load, we also have got tangential load which might be acting on the tool or the workpiece, whatever it is placed on the top of this dynamometer. So due to this action of Ft, rather than deforming in this manner, it may roll, like due to the action of Ft, this thing may roll. So due to the action of this force, it is undergoing some amount of deformation and some amount of deflection. So due to this Ft, it is undergoing some amount of angular movement or angular displacement, and as well as that as well as some deformation, say delta, which can be in the form of angle, so angular deformation I can say. So but you need deflection rather than deformation to calculate Ft, right? So that's why we generally don't go with ring type dynamometers, because they are not having this proper stability, since they can roll off easily under the action of tangential loads. That's why we don't go with circular ring structures. Coming to the next question, which type of dynamometers are most suitably used for grinding force measurement? So under grinding loads, you need to have a setting which is stable, which is capable of withstanding the high loads, and it's also rigid. It shouldn't have the tendency to buckle. So you can see here, these are the criteria for any dynamometer. Along with that, it should also be sensitive. So that is the most important thing, rather the primary requisite for any dynamometer. So which type of dynamometers are suitable for grinding force measurements? Cantilever type. So mostly we use cantilever type for turning operations. It is suitable for those type of settings. Circular ring type and octagonal ring type. So circular ring type is, as I said, it's not stable. So due to its instability and rolling tendency, we don't use it. We generally replace it with octagonal ring type dynamometer, which looks quite like this, as we had discussed. However, for higher loads, like during grinding operations, suppose we have larger slabs. In that case, using a single dynamometer like this won't be a stable option. Like this, under the action of this grinding loads, this won't be able to record the forces properly, or record the strains rather properly, and along with that, it may also you know get dislodged from its position. So due to insufficiency of rigidity and its base for location, this particular thing, insufficient base for location, it may not be able to measure the forces properly. So that's why we generally take another one like this and we join them. So the joining is being done in a proper manner like this. So this is your solid portion, and you have a hanging hollow portion in this in between, and you place your strain gauges. So these four strain gauges will be useful for measuring the vertical force, and these four strain gauges will be useful for measuring the tangential force. So the correct option would be extended octagonal type ring type dynamometer. Coming to the next question, tool life reduces for rake angles larger than the optimal one, because, so as we know that suppose this is my gamma rake angle, and on the y-axis I have tool life. So if we increase the rake angle, initially the tool life increases, but after a certain value, it again starts reducing. This happens because the material gets weaker as we are increasing the tool angle. So this is my gamma, this is my alpha clearance angle, and this is my tool section. So as we are increasing the tool angle initially, what happens? We are actually reducing the shear area by lessening the shear length. So as the shear length is reducing, so in the first case, your chip would look somewhat like this. So this would be your shear length. But in the second case, your chip would look something like this. So this will be your shear length. So as you can see that the shear angle has increased and the shear length has decreased. So due to this reduction in shear length, the shear area is also getting reduced. And we know that the cutting force or the shear force, we can say that it's tau s into as. Since a is getting reduced, this fs is also getting reduced for a given shear strength for a given material. And as a result of this reduction, cutting force is also getting reduced. So you need less force to deform the material. So that is the reason why increasing the rake angle will give you a higher tool life, because you are you're subjecting it to less uh, forces, less cutting forces. So that's why it's the tool life is increasing initially. But at the same time, you can see that if you are reducing this particular section of the tool, the material that is holding the tool, that itself is reducing. The tool material is reducing with increasing the rake angle, and as a result of which, under high dynamic loads, this tip of the tool may chip off due to this reduction in the material. So the reduced resistance towards this dynamic load under chattering conditions will increase the chances of tool failure. So after a optimum value of gamma, which is the rake angle, your tool life again reduces. So what are the reasons? So as I said, that chipping off of the cutting edge, this is one of the correct options. Tool edge gets weakened. Yeah. Cutting force acting on the tool increases. No, cutting force is not increasing because of the strain hardening of the workpiece material, because of larger temperature accumulation in the tool. So we can see that as the tool, this particular region, it's reducing uh, due to the increase of rake angle from here to here. So the area that was initially available for the dissipation of the heat energy from the cutting area, that is getting reduced. So this is my new section of the tool, and it is having lesser area for the dissipation of energy or dissipation of the heat. So hence a larger portion of the heat gets accumulated, and it leads to increasing of temperature in that region. So 1, 2 and 5. So my option B is the correct option here. If you are having any doubt, you can stop me and you can ask any questions. Okay. So we have a basic numerical. So the tool life equation for machining C40 steel by HSS tool is given. So this should be Vt power n equal to constant. You are given with two conditions. You should be careful about the units, because this, your V and C should be having, sorry, your C should be having the units such that V and T are also maintained, right? If we are taking V as meter per minute and T as minute, accordingly the units for C will change. So generally it's like V is meter per minute and T is minute. T is taken in minutes. So yeah, you are given with two conditions for the same tool. So all you need to do is just plug in the values of the two conditions. So 25 into 90 to the power n is equal to C, and in the other case you have 35 into 20 power n is equal to C. So basically, if you if you have come across this graph, it's log V versus log T, then you can see that your Vt power n curve actually looks like this. If you plot it on the log scales, it is actually a straight line. It's nothing, just we are introducing log on both sides. So we have log V plus n log T is equal to log C. So this will be my log C rather. Okay. So you are given with two conditions, here and here. So to calculate n, n is the slope of this one, of this curve. Log of V2. V2 is nothing but 35, say, minus log of V1, that is 25 divided by, so 1 and 2 you need to be careful. Like if this one I have taken as 1, this one I have taken as 2, so log 20 minus log 90. So what are the values that you are getting for this particular case? Yeah. So 0.223. Okay, so now you need to calculate seeds and just put the values in one of the expressions. So 25 into 90 power 0.223, 68.5. So what will be the unit of C? You can plug in here and see. It won't be unitless. Okay, so there's a second part to this question. So I have made a mistake here. See, this one will be 25 minus 95. So if you see this particular expression, I have just put log on both the sides and equated them. It's log 25 plus n log 90 is equal to log 35 plus n log 20. So you take the n on one side and just calculate the slopes. You will get you calculate the value of n. You will get this. So there's a second part to this question. I recommend the cutting speed for 60 minutes of tool life. So I'm doing it here itself. So my V is, you need to calculate V. So V into 60 to the power 0.223 is equal to 68.5. From Vt power n equal to constant, you can write this. So my V will be 68.5 divided by 60 power. It will be around 27.5 meter per minute. Okay. So I think, yeah, that's it for today's session. If you are having any question, you can ask me now. We just solved a couple of numericals and a few theoretical questions pertaining to last week's video lecture. Hello, am I audible? Hello, am I audible? Can anyone just confirm, please? Because I think I have lost my internet connection. Akshay, I can see you're here, so uh, just confirm if I'm audible or not. Dr. Borad M. Hello, Dr. Borad M. I can see your logo. So can you please confirm if I was audible or not? I mean, I was just presenting. That's why I'm just asking it. Anyway, I hope that we could address a few questions through this live session. We will meet again in the next week with some new problems. And if you are also having any doubt regarding your assignments or any other questions related to this particular course, then you can tell me, and we can discuss it in the upcoming lectures. Thank you.